Thermodynamics as a general topic involves heat flow and energy flow in chemical reactions and in physical processes. And we're going to focus on two factors as parts of thermodynamics in this particular lecture. I'm going to talk about enthalpy and I'm going to talk about heat capacity. So enthalpy itself, it's a fancy word, and it's just talking about heat energy. You experience this all the time. So heat energy, this is what is coming off of a fire when we have a campfire. That's heat energy being released from a chemical process. And that's a particularly dramatic chemical process where lots of heat energy is released all at once, but most chemical reactions and physical reactions involve much smaller amounts of heat energy. So enthalpy as a general topic is heat energy that is released or absorbed during physical and chemical processes. So this involves phase changes. You may not have noticed the energy that's being absorbed when you put an ice cube into your iced tea and then it melts, but that is what is making your iced tea apparently cooler. The ice cube is absorbing energy from the iced tea and it is converting the solid water into liquid water. So you also don't notice when you are dissolving sugar in your coffee, if that's how you like your sugar, if that's how you like your coffee. If you are mixing things, this can absorb or release energy, but usually they're very, very small amounts and you don't really notice them. And then chemical reactions are the most dramatic ones. Not all of them have dramatic amounts of energy that are released like in combustion reactions, but this is a common place where energy is absorbed, almost, or released. And this is just a few of the most common types. I'm not going to make a comprehensive list here. So the other thing that I want to point out about enthalpy, and for enthalpy, we use the letter H, capital H, to symbolize it. Enthalpy is a state function. And this is a special type of function where it doesn't matter how you get from state A to state B, the energy change is the same regardless. So if state A is, my reactant and state B is my products, then it doesn't matter which path I take to get from A to B or B to A, the amount of energy is the same. So in enthalpy, this is a very useful, with any state function, this property is a very useful one because it means that sometimes there are quantities that we can't directly measure, but we can use other quantities. And the main way that we talk about doing this is with something called Hess's law. And Hess's law is just an illustration of the fact that this is a state function. So we can use other enthalpies, other paths, to calculate the enthalpy of a reaction. And I'm going to use the symbol here. Delta here, this triangle is delta, which is change. And then H is the enthalpy. And then we often put a little subscript, and the location of the subscript can vary. Sometimes you will see the subscript to the right, sometimes you'll see it in the middle. They are all equivalent to each other, and R is just for reaction. So you're going to see a lot of different subscripts. I don't want you to get too tied up in the subscripts. These are just for convenience. This is the same. This delta HR is the same as just any delta H. We're just being specific about which delta H. And this is useful because we have so many different processes that have enthalpy. And so it's easy to get confused if I don't start labeling those sub H's or sub R's or sub F's or sub C's. It can be easy to mix them up. As long as you're careful, it doesn't actually matter whether or not you use any subscripts. All right, so one of the easiest ways to illustrate using Hess's law is to do calculations using formation enthalpies. Okay, so formation enthalpies are listed as delta sub H, or excuse me, sub F H. And often you'll see it with a little bubble right here. This little bubble means that this is in the standard state. And the most important part of the standard state is that this is at 1 bar of pressure. And this is helpful because basically all chemical reactions we do, or almost all chemical reactions we do, are on the benchtop in the lab, which is at atmospheric pressure, which is effectively 1 bar. So it means that we can use these numbers when we are in a lab setting and not at some pressurized setting. The temperature is specified in the problem or in the table. And then there are some details with the standard state in terms of like what the concentrations are, but for the most part, we don't need to worry too much about them right now. So formation enthalpies come from formation equations. And a formation equation is making 1 mole of a designated product, whatever we're interested in, from stoichiometric amounts of elements, pure elements, no compounds on the reactant side, in their natural elemental form at that temperature. Okay, so I'm going to go ahead and write an example here. So a product that I might want to make, and you can write this for anything, I just thought one would be with some different ratios of things might be fun. So let's talk about making some ammonium hydroxide. Ammonium hydroxide is most commonly experienced as an aqueous solution, so let's go ahead and make it aqueous. So this is our product. So we want to make 1 mole, and that's why there's no number right here, because anytime there's no number in front of our compound, that means it's automatically a 1. So if I look at my elements, I see I have N, nitrogen. Nitrogen in its natural elemental form comes as nitrogen gas, as N2, but I only need 1 nitrogen here, and so I'm actually going to use a fraction to say I want 1/2 of a nitrogen gas. I know it sounds a little funky. This is just the way that we define formation equations and how the enthalpies work out. So then I look at hydrogen. I have 4 hydrogens here and 1 more here. So I have a total of 5 hydrogens. Hydrogen also comes as a diatomic gas, H2. So if I need 5 of them, that means I'm going to need a little fraction. I'm going to need 5 halves, or 2.5 of these molecules. So that takes care of my hydrogens. And then oxygen, I need 1 oxygen. So this is the same situation as for nitrogen gas. And I need 1/2 of an oxygen gas to get me to 1 mole of my product. So this would be a formation equation, and I would find a formation enthalpy in a table. And I can look this up, and I'll look at some tables in a little while. So if we look at another example of, I don't know, like maybe sodium carbonate as a product that we might make. Okay, sodium carbonate is a solid. So if I look at sodium, I need 2 sodium atoms, and sodium is a metal. And you may not think about it too much as a metal, but it is. And so therefore, it's just going to show up as sodium single atom, and we need 2 of them. Carbon has a couple of different forms, so they're solid, and we are probably going to put graphite. It's also fine to just put solid, but solid graphite and solid diamond are 2 different solid forms of carbon, and it is the graphite form that is the natural elemental form. So if you want to be really super careful, then you can write Gr for graphite. It's also totally okay to just put S for solid. And we need only 1 of those, and so again, carbon is in single atoms in our equation. That's fine. All right, so here we come to oxygen again, and oxygen is in this O2 form, and so we need 3 of them, so that's going to be 3 halves. So those are 2 examples of formation equations where we take stoichiometric amounts of each element in its pure elemental form and make 1 mole of product. Right? 1 mole. And I want to point out again that there are no compounds over here on the reactant side. We are pure elements. And that is how a formation equation is defined. Okay, so formation equations are very helpful to us because we are going to use formation enthalpies to calculate reaction enthalpies. So let's look at a chemical reaction. So if we are looking at the combustion of butane, for example, butane is C4H10, and it's in a gas form. It's what would be in a cigarette lighter if you have any experience with those. And we would always assume that we would have complete combustion and turn it into carbon dioxide, gas, and water vapor. Because it's a burning reaction, it's not going to make liquid water. So that's how I remember that one. So if I balance this out, you can either balance this and use a fraction here, or you can double it and get rid of the fraction, and however you write it is fine. Okay, so you just make sure that you write it balanced and everything else will work out. Okay, so I'm going to just go ahead and look at this second version of it, so I don't have to deal with any fractions here, but it's fine either way. So we know that this is the path that we are talking about. This is a direct path where I would take this compound, butane, burn it in oxygen, and make carbon dioxide and water. So this is my path, and it would have some reaction enthalpy. But I also remember that each one of these materials, I can undo my reactants. So if I undo butane into its elemental components here, this I'm really going to have to double because I have 2 out there. So if I undo this 2 butane molecules, then I'm going back the direction of -2. So I'm going from the product of my formation equation back into the elemental reactions. And when I go forward for one of these reactions, then this is a certain amount of enthalpy for the formation. And if I go back the other direction to undo a compound and make it into its elements, it's exactly the same amount of enthalpy involved, only with an opposite sign. So anytime I want to use Hess's law using the formation equations, then with my reactants here, I'm going to undo them into their pure elemental form. So I'm going to have 8 carbons, and I'm going to have 10 H2s. And the amount of energy to undo 2 butanes is just -2 times the enthalpy for the butane, enthalpy of formation. and pay attention to phases. Okay? So then I'm going to take oxygen, and oxygen, this is an interesting case here because oxygen is already in its pure elemental form, and so I need a little side note here that the enthalpy of formation of any pure element in its elemental form, or in its natural state, is equal to 0. So I can say this is minus 13 of the formation enthalpy of oxygen, but I'm going to put a little note here that this is equal to 0. All right, so I have taken apart the butane. My oxygen was already in its natural state. Now I'm going to allow them to react together. I'm going to take 8 carbon atoms and 8 oxygen molecules, and I'm going to recombine them to make carbon dioxide. And the amount of energy to do that is 8 times the formation enthalpy of the carbon dioxide. And then I'm going to take my 10 hydrogens that remain and my 5 O2s that remain, and I'm going to recombine them as 10 waters. And the amount of energy to do that is just 10 times the formation enthalpy of the water. Okay, so if I add up all of the energies from this process, I know that this is a separate path, right? I already said that this direct path has one amount of energy, but I did the same thing. I took my energies here, I just took them apart, recombined them, and then put them back together again. So this is a second path, path B, and the energy, the enthalpy, for path B is equal to the energy for the direct path. So I can just do that. I will see that the energy for my reaction, which is the same as the energy of path B or the direct path, is equal to minus 2 times the enthalpy of formation for the butane minus 13 times the enthalpy of formation of the oxygen plus 8 times the enthalpy of formation for the carbon dioxide gas plus 10 times the enthalpy of formation for the water vapor. So if I look up those numbers from a table, then I can actually calculate what that number is. So I already looked them up for you. I'm just going to plug them in, and I'll show you a table in a little bit. So this enthalpy was minus 126.15 for the butane. Pay attention to signs here, they're really super important. And then we have minus 13 times 0 plus 8 times minus 393.509 kilojoules per mole plus 10 times minus 241.818 kilojoules per mole. And so if we add all of those up, we get minus 5313.95 kilojoules per mole, and I'm going to keep 2 decimal places because we're doing addition, and the enthalpy of formation for the butane has 2 decimal places, and that's the smallest number that we have. So if we look at this number, and we think about the fact that this is a combustion reaction, this enthalpy of reaction is large, it's exothermic, and if we're thinking about the fact that we're burning something, that makes perfect sense, right? We expect that a combustion reaction will be exothermic, it will release energy, it'll have a negative sign right here, and that if we're burning something, it probably is going to be a fairly large amount of energy, okay? So if you have seen other explanations of enthalpies of reaction, You might have seen something that looks like products minus reactants as how to calculate that. And this is exactly what we just did. We changed the signs on our stoichiometric coefficients for our reactants to negative, and the negative here is because we are using up reactants. So if you like thinking products minus reactants and that works for you, awesome. Just don't forget about the stoichiometric coefficients and make sure that you don't change the sign twice, okay? So I already put the negative in the coefficient right here, and that is taking care of that minus the reactants part. Another way that you might see this represented is you might see it as the summation. That's what this big capital sigma is, from 1 to n of nu sub I. And in this case, this is again exactly what we just did. This summation means all the things. So all the reactants and products are labeled 1, 2, 3, 4, 5, 6, however many we have. These are the stoichiometric coefficients. And the reactants have negative stoichiometric coefficients. And then these are the formation enthalpies for each of our individual chemicals, just like we looked up in a table. Okay, so any of these are reasonable ways to think about it, and if you have some additional way that you've already been taught and it works for you, that's totally awesome. Just stick with it. So let's go ahead and take time for another example. I'm going to suggest that you pause the video and take a look and try this reaction. So in this reaction, this is going to be the reaction of ammonia gas with oxygen to make nitric oxide, which is an air pollutant, and water vapor. Okay, so why don't you go ahead and pause the video and then use the thermodynamic tables in the review section of the Moodle and look up the enthalpies of formation and solve this problem, and then come back together and we'll check our work. All right, so hopefully you already did this work. So if we calculate these enthalpies, I'm just going to plug in the numbers here. My stoichiometric coefficient is -4 because it's a reactant, and then the enthalpy of formation for ammonia was -45.90 kilojoules per mole. Water is 0 again. Nitric oxide is positive 90.29 kilojoules per mole. And water vapor is -241.83 kilojoules per mole. So if you add these all up, you get -906.22 kilojoules per mole. If you had a slightly different table than the table values that I used, don't worry about it as long as it's really close to the answer and these numbers are really close. The only thing that you might need to be careful of is to make sure that you are using the appropriate phases. Sometimes, like with water especially, you will have liquid water available and its enthalpy of formation is only a little bit different than the gaseous water vapor. So just make sure that you're paying attention to the phases when you do these calculations. Okay. When we are talking about enthalpy, we're commonly using enthalpies of formation to calculate enthalpies of reaction, but we also need to pay attention to the fact that enthalpy or heat flow happens all the time. So heat flow happens when we do mixing, and it happens, if a gas or a liquid dissolves in another liquid, or a solid dissolves in a liquid. When we have a phase change happening, Every single physical and chemical change involves heat flow. So I'm just going to remind us that heat flow happens all the time. And we've been talking specifically about chemical reactions, but we add and remove heat from systems all the time too. And energy is involved in that. So if you are a coffee or a tea drinker, let's think for a second about if we were getting ready to make our coffee or our tea, and we get some water and we put it in our kettle and we put it on the stove, and then we heat it. And we have water, and depending on how much water is in our kettle, this affects how much time it takes to heat that water. We are flowing energy in from our stove, or if you have an electric kettle, from the electric burner that it has there. I guess it's not really a burner, but the electric coil that it has. And so if we think about all of the energy that we are involving in boiling this water or heating it to whatever our appropriate temperature is, the goal is not to transfer the water that's liquid into gaseous water. Our goal is to increase the temperature. At the same time, we also know that this kettle is also going to get hot at the same time. So the amount of energy, I'm going to say heat energy just to be really specific, that we need in order to heat our water in our kettle is going to depend on two things. The type of materials. What's my kettle made out of? Is it conducting heat really well? Is it really heavy? Is it really lightweight? So the type of materials and also the amount of material. Did I put a lot of water in my kettle? Did I just put a little water in my kettle? Is my kettle super lightweight and easy to increase the temperature, or is this going to take a lot more? So these are the two factors in here. And when we look at changing the temperature of a system, we're going to calculate it based on the change of temperature that we are interested in and the heat capacity of the material. And sometimes the quantity of the material. I guess there were three parts there. How much we want to increase the temperature or decrease the temperature, as the case may be. Okay, so heat capacity has another term. Sometimes we call it specific heat. Sometimes we call it specific heat capacity. All of these things are exactly the same. They vary by convention only in units. Oops, not kilojoules usually. Heat capacity will usually have units of joules per mole Kelvin. Specific heat will usually have units of joule per gram Kelvin. So it's just looking at whether or not we have molar quantities or mass quantities. And really, this is not a hard definition. This is just a convention. They really are exactly the same thing. And you can convert one into the other because, remember, our molecular weight is gram per mole. And so we can use the molecular weight of a material to convert between these two guys, gram per mole. Okay, so our heat flow to do a physical process is conventionally, we use a Q to talk about it. Really, this is just a delta H. and we say that it is the heat capacity, C, times the change in the temperature, sometimes multiplied by the mass or the number of moles, if you, depending on what kind of units you want. Okay, so if I do this calculation, my heat capacity here is going to have units of joules per mole Kelvin. My temperature change will have units of Kelvin, and my moles, in this case, would have units of moles. And so if I multiply these through, this should give me units of joules. I also could calculate just Q times delta T, and this would give me units of joules per Kelvin, joules per mole, or joules per gram, depending on what my heat capacity was. Okay, so I want to say a little tiny bit about our heat capacities. Heat capacity, this is another C. Usually it's a capital C. And you will also see it as CV or CP. And you will probably see little bubbles for the standard state. This is the constant pressure heat capacity, and it's the most common one you'll see. In the constant pressure heat capacity, that constant pressure part of it, this means, again, that we are doing it under laboratory conditions where we're not controlling the pressure, but instead we're just doing it at atmospheric pressure, and therefore it's just going to be at 1 bar automatically. Okay? So our heat capacities excuse me, are going to be useful for helping us calculate the amount of energy flow that is involved in a heating or a cooling process. And the final part that we need to talk about is phase changes. So phase change, we're typically talking about solid, liquid, and gas. And these are all reversible, right? We can take an ice cube and melt it, and we could evaporate it, and as long as we collected all the gas, we could turn it back into a liquid and turn it back into a solid, and they would be identical to each other. So if I'm going from a solid to a liquid and I'm wanting to melt that solid, I'm going to have to put some energy in. And the same is true if I want to go from a liquid to a gas. I have to put energy in. And this has to do with the fact that a solid is a condensed phase, and it has chemical bonds, and if I am going from a solid to a liquid, I am breaking those chemical bonds. And even though the liquid still has intermolecular forces holding the material together, so it's still a condensed phase, that still requires energy that I have to flow in to turn it from a solid into a liquid. And the same is true for a liquid going to a gas. And so usually the vaporization enthalpy is probably bigger. I don't even know if I need to say usually. I think it's always bigger than the enthalpy of fusion. So that's what this enthalpy is. It's the enthalpy of fusion to go from a solid to a liquid. It's enthalpy of vaporization to go from a liquid to a gas. And the vaporization enthalpy is usually quite a bit bigger than the fusion enthalpy because it takes a lot more energy to break these condensed phases apart into gases where the particles are not really interacting at all. So, but if we, I just said this was reversible. So if I go back from a gas to a liquid, then energy is going to flow out of my system instead. And it's going to be the same amount of energy as this vaporization enthalpy. It's just going to be the opposite sign. And the same thing is true if I go from from a liquid to a solid. If I let that freeze again, energy is going out. And it's going to be the same amount. It's going to be minus the fusion. It's getting too messy there. The enthalpy of fusion. Okay, there's also one additional phase change, and that is to go directly from a solid to a gas. And since these are reversible, the interesting thing, this is called sublimation. And this makes a lot of sense, that if I want to go directly from a solid to a gas, it's going to take me all of the energy to make it a liquid and then all of the energy again to turn that liquid into a gas. You just do it all at once. So this is just a sum. So when we talk about these phase changes, I just want to kind of summarize the different types of heat flow we've discussed. That you can calculate. One of them are for chemical reactions. The next one was for heating or cooling. And the third one was for phase change. So when you are thinking about a thermodynamic reaction that's involving energy, I encourage you to come back over here and think about which of these kinds of heat flow events am I talking about? And maybe I'm talking about more than one of them. But try to classify them for yourself, because then you will know how to approach this problem. If you have a chemical reaction, then we are going to use our enthalpies of formation and calculate the enthalpy of the reaction. If you are using heating and cooling, then we are going to use heat capacities. If we have phase changes, then we are going to use these enthalpies of fusion or vaporization or sublimation as is appropriate. So it's always a great idea to think about what are the heat flow events that are happening in here, which of these classes am I using, and therefore which of these numbers do I need to look up.